Hey friends, welcome back. So today we want to take this innocent looking problem and use it to launch a discussion on continuity. So we've got this piecewise function. The input variable is t, so we see the t here and here. Cool. This k, where k is a constant. So when I taught math in the United States of America, I found that a lot of my students had trouble with this phrasing right here. And at some point, I'll make an entire video ranting about why I think it's an issue and how to resolve that issue. But for now, I just want you to know that whenever you see this phrasing where something is a constant, that's just telling you, hey, look, this is the variable t. It's going to change all over the place and assume all the different values. K, we don't know what the number k is. But once we find it, it's no longer going to change. That's really what this is saying. But how does that affect you and your problem solving? The answer is it doesn't really. Okay, so you can safely ignore this. It's just a technicality that we, like to put in math problems. Okay, the real part of the problem is find the value of k, right? Because we don't know what k is, such that, and this is the condition we're trying to meet, that f of t is continuous everywhere in this word. Okay, so I have not formally defined continuous yet. I have alluded to it and promised that at some point we would discuss the technicalities. So that's going to be today. In order to get there, let's start with a discussion on what this graph looks like. Okay, so first things first, what I want to do is I want to show you guys on the TI-84 a little trick with piecewise functions, right? Because we could graph this by hand, but we might as well look at a calculator. So I'm going to go into y equals, and here I'm going to have these plots. So I'm using x as the independent variable instead of t, because that's the default of the TI-84. And so here I have effectively t plus k. Now see this funky business? I have divided by this x less than or equal to 19. So on the TI-84, the less than or equal to and all the other logic symbols are in second. And if you hit the math button, you see that blue text that says test. This is where these guys are. Okay. So if I were to say something like, is 5 greater than 2? This is a yes, it is a true statement. So what the calculator will do is it will resolve this as 1. It's giving us a Boolean. Okay. But if I were to say, hey, is 6, second math, equal to 4? The answer is no. This is a false statement. So the calculator will give us a 0. Okay, so put that into what's happening in here. Okay, so if x is less than or equal to 19, this test will resolve to 1. So I'm effectively taking x plus k divided by 1, which is just x plus k. But if x is not less than or equal to 19, so if like x is 20, for example, then this will give me a 0, which means I'm dividing x plus k by 0, which gives me undefined. So the calculator simply won't graph x plus k once x is bigger than 19. And the same deal down here. So I don't actually know if this was the intended way for us to graph piecewise functions, but my high school calculus teacher showed me this, and it's seriously some five-head shit, okay? So we go back, and here I don't have a value for k, right? Because the entire point of the problem is to figure out what k is. So what I'm going to start doing is I'm just going to, punch a number in the place of k and see what happens, and maybe we'll gain some insight. So I'm going to do this by hitting the number 4 and hitting the stow button down here. This stores the value of 4, hit alpha, hit k. When I hit enter, now the calculator understands that anytime I use the letter k, I actually mean the number 4. I'm doing k equals 4. Right, so I, didn't change anything here. It still says k, but when I go to graph it, and I've graphed it in a window that's sort of meaningfully appropriate here. So the scale is tens, and x is going from a little bit basically 0 to 30, y from negative 50 to 100. So what we're seeing here is that jump right there is occurring when t gets to 19. Okay. This is an example of a function that is not continuous when t is 19. Okay, which then begs the question, okay, so what does it mean to be continuous? The way we intuitively understood it was if the graph is sort of connected. We often say this as if you can draw the graph without ever lifting your pencil. So there's no hole, aka removable discontinuity. There's no jump discontinuity, meaning you jump from one value up to another. There is no vertical asymptote. And there are some other very interesting things that math people come up with that technically qualify as, I shouldn't even say technically, they qualify as discontinuities, right? Those exist, but for our purposes, if you can draw the graph without ever lifting your pencil, that's sort of what we want to consider continuous. So we look at this and say, well, that's not continuous. Okay. Well, what could we change? Well, we could certainly maybe take the number 1.5 and store that in the variable k. All right. And we're going to regraph this. So we still see this jump. We call this discontinuous, but it's sort of getting closer. And in fact, if we think to ourselves, wait, what if those two actually connected? Then maybe we would call that a continuous function. Okay, so let's sort of formalize this idea. So what we've got here is, this is the y value, this is the t value, and here at 19. So we've got some interesting business. We've got a closed circle here. And we've got an open circle here and something like this. Obviously a little bit exaggerated. Okay, we're thinking if I can take that and instead of having a different location for the open circle here and the closed circle here, what if they were overlapping each other? As in, what if my graph looked like this? Maybe that's what we want to call continuous. Okay? So the definition is the following. We say f of x is continuous at the value x equals c if and only if three things are true. So, number one, f of c has to exist. So we actually have to have a y value. So an example there of f of c not existing would be, what if we had just straight up a removable discontinuity? So there's no y value. Or what if we had a vertical asymptote? That would be another example of not having a y value. Okay. So first of all, we need a y value. Second of all, we need the limit of f of x as x approaches c to exist. And we remember, having a limit exist means I have to approach the number c, I guess x has to approach the number c, from both sides. So the one-sided limit from the right and the one-sided limit from the left have to both be a single number and they have to match, right? So in this case, right, we could say, just staring at a graph, if I approach the number 19 from the right and I approach the number 19 from the left, it looks like I'm approaching the same value. In that case, I would say the limit of f of x as x approaches c does exist. It is a single number. And finally, the most important part, that the limit of f of x as x approaches c has to actually equal the y value at that point. So if I have a hole, then this will not be true, right? Because if there's no, if this value doesn't exist, so if it doesn't exist, then nothing can equal a thing that doesn't exist. Okay. Now another weird example of this would be, what if I had a function that was defined so that I have a hole right there at t equals 19, but the function is actually defined up here. So this would be a case where f of c does exist. F of 19 would be that y value up there. The limit of f of x as x approaches c also exists. I'm approaching the location of the hole, but this right here, the y value of the hole, is not the same as the y value output of the function. So we would say, in this case, f of x, or I guess f of t for the drawn graph, is not continuous at that t equals 19 value. So this is the formal definition. Okay. Perhaps it will be useful for us in the future if we just go over a lot of different examples on, what is a continuous function at a certain point, what is not a continuous function at a certain point, and deal with that. Maybe test review. Okay. But for now, we're focused on this problem right here. Okay. We need f of t to be continuous everywhere. Well, this right here is a linear function. And for now, we're going to take for granted the fact that any linear function is continuous over its entire domain. In fact, any polynomial function is continuous over its entire domain. And we haven't proven that. I haven't even talked about how we would prove it. We're just going to take it for granted for now. Okay. So this linear function is continuous everywhere on its domain. This is also a linear function. We don't know what k is, but it's a number. A number times t is a linear function, and the slope is k. Okay. Also continuous everywhere on its domain. The only place where we could potentially not be continuous, as we see on this graph, is at the transition between these two pieces in the piecewise function. So what we need to do is to connect those two pieces so that we approach the same number from both sides, right? Hence we have a limit, and the number we approach from both sides actually matches what the function outputs, okay? That they both exist and they match. Let's see how that plays out. So to restate what our goal is, we are trying to find the value of k that makes this f of t function continuous everywhere. And really, we are only concerned about f of t being continuous at the transition t equals 19 because everywhere else f of t is automatically continuous. Okay. So the three things we have to establish to prove that f of t is continuous at t equals 19, right? We're going to do it in the following way. So f of 19, well, when t is exactly equal 19, I don't look at this down here. I'm going to be in this condition, so I'm looking at this piece of the function. So I would say, oh, f of 19 would be the value of t is 19, 19 plus k. All right, I don't know what k is, which means currently I can't evaluate this to a number. Now I look at the limit of f of t as t approaches 19. In order for that limit to exist, I need the limit as I approach from the left when t is a little bit less than 19, and the limit as t approaches from the right when t is a little bit bigger than 19. I need them to match. Okay. So I'm going to write it like this. The limit of f of t as t approaches 19 from the left. My t is a little bit less than 19, so I'm going to look at this right here, which is going to be the limit as t approaches 19 of this t plus k. Now, incidentally, this is a linear function, and so we can also just kind of look at the graph, right? Here, as I approach from the left, as I get toward 19, I'm approaching the y value that would occur if I just took the number 19 and plugged it in here. That's what happens when you're dealing with these sort of simple linear or polynomial functions. So that would be 19 plus k. All right. Then if I consider the limit of f of t as t approaches 19 from the right, so t is a little bit bigger than 19, I need to be looking at this bottom piece. So this is the same thing as writing the limit of the expression kt as t approaches 19 from the right. Once again, this is linear. So glancing at the graph, this is sort of along that red line. I'm approaching from the right, but the y value that I'm approaching is really just the y value that would occur if I plugged 19 in for t. So this is k times 19, also known as 19k. All right, so I know that k is a constant. It's a number. So I know this number exists. I just don't know what it is. Now here's the deal. These two are supposed to match, but I haven't actually proven that they match yet. In fact, that's what I need to force. I need to force these two things to match in order for this to exist. Oh, so that's really the whole point of this problem, right? So if I take this and go, let 19 plus k equal 19k, then I can do some algebra and say, okay, I subtract 1k over, that's 19 is equal to 18k, and I divide by 18, and I end up with k is equal to 19 over 18. This is the value of k that would cause the limit of f of t as t approaches 19 to exist. Now, if I want to be very formal, I can go and say, okay, let's actually demonstrate that this works. Well, so the limit of f of t as t approaches 19 is going to be either of these. They're both equal to each other. So I could just as easily go, hey, this is going to be 19 multiplied by the value of k, which is 19 over 18. Is this equal question mark to f of 19? Well, that's going to be here 19 plus 19 over 18. Where am I getting that from? That's the 19 there, and k, I'm claiming, is 19 over 18. All right, and I guess the question is, are these two things the same? This is going to be what? 361 over 18 on this side equals question mark. So I have to common denominator this. This is what? 342 over 18 plus 19 over 18. And they do indeed match. Let's just to make sure, we'll confirm with the calculator. What do I have? I have 19, I'll click 19 multiplied by 19 over 18. So that's a number. And on the other side, I've got 19 plus 19 over 18. Do I get the same thing? Cool. To the end of the display, they look the same. All right, and hopefully you believe that there. So now, just for funsies, let's see what happens to the graph when we actually make k equal to this number. So we're claiming that k needs to equal 19 over 18. So we're going to store that in the letter k, and we're going to regraph and see if we have agreement. All right, and it looks like at that point, the two pieces fit together, and we have a continuous function. So f is continuous everywhere to the left, everywhere to the right, simply because each of these is a linear function, and we're taking for granted that linear functions, and by extension polynomial functions, are continuous everywhere on their domain. If we can make the junction match, as in if we can prove that f of t is continuous at t equals 19, then we can extend this idea and say, therefore, when k equals 19 over 18, f of t is continuous everywhere. So another example of the same thing, we've got this piecewise function. X is the input variable. K is a constant that we don't know. We're trying to find the value of k such that g of x is continuous on the interval from 0 to 5. And we notice here, right, the domain of g of x is from 0 to 1 and then 1 to 5. So really it's from 0 to 5. And glancing at this is linear. This is also linear. That means our function g of x is continuous everywhere automatically except potentially the part where x is actually equal to 1. So we're transitioning between this piece and that piece, right? So that's really what we need to focus on. If we can make g of x continuous at x equals 1, right? So if g of x is continuous at x equals 1, then g of x is continuous on the interval from 0 to 5. That's really what we're saying, okay? So this is the piece we have to establish. Now, whenever I ask students, okay, so what do we do? Oftentimes, my students will respond by saying, well, don't I just take the number 1 and plug it into the top, plug it into the bottom piece, and just make them match? And that student is not wrong. Okay. In pretty much all of the cases that I've seen that you encounter at this stage in calculus, it simply comes down to take that number, plug it into the top piece, plug it into the bottom piece, make them equal, and there you go. So let's just try that, right? So if I take the 1 and put it up in here, what am I putting in for? X. So it's going to be k times 1, right? So that's going to be k times 1 is equal, and put 1 in for the x here. So that's 2k times 1, 2k plus 3. And then I solve for k, so I'm going to end up saying that k is equal negative 3. Or I can subtract 2k over, get negative k equals 3, then, yeah, whatever. Okay, so that's my conclusion. So what am I actually concluding here? I'm claiming that if k is equal negative 3, then g of x is continuous at x equals 1. That's my claim. Okay, and it turns out I'm not wrong. And the student who proposed this is also not wrong. Now the problem is, if you have to do this on paper, show your work, and submit this for credit, you will probably not receive full credit simply for showing this, because continuity is a little bit more technical. Even though what you did is not incorrect, you haven't addressed the full definition of continuity. So when you're doing this for like an online assignment, sure, feel free. You're just going to take this number, plug it into the pieces that meet when x equals 1. So if there's like 3 or 4 pieces, you're going to pick the 2 pieces that you're transitioning between at the value. Okay. And just plug in that value to the x, set them equal to each other, solve for k. That will get you the answer. Okay. But I want you to remember that sort of behind the scenes, what's actually occurring is you need to demonstrate that, number 1, g of 1 exists. Okay, you need to be able to take x equals 1 and plug it into the function and get an output. So we have to approach the branch or the piece where x is actually equal to 1. So I would plug it into here. Okay, and I would say that's going to give me k times 1. I also have to demonstrate that the limit of g of x as x approaches 1 exists. And anytime you have to show a limit exists, you sort of have to consider the limit as x approaches 1 from the right, g of x, is equal to the limit as x approaches 1 from the left of g of x. So meaning you have to think about what happens when x is a little bit bigger than 1. Hence you have to look at this piece, right, and take the limit. You also have to consider what happens when x is a little bit less than 1. So you have to look at this piece, because that's when x is less than 1. And you have to make sure that those limits match. And then finally, you have to demonstrate that the limit of g of x as x approaches 1 is actually equal to the output value of the function that you got up here, right? You have to establish these 3 things to have technically established continuity. The thing I did on the previous problem is what you want to do if you're doing this for an exam or for a homework that you're turning in, okay? This is not wrong, but I want you to understand that this often will not get you full credit, and the reason is it's a little bit more technical than that. Cool? All right. Well, thanks for listening. Peace.